Hello, good day, and welcome to my video tutorial. Now, these are the three gas laws that we have looked so far. We have the Boyle's law, we have the Charles law, and we have the Gay-Lussac's law. Now, each of these gas law will tell us that whenever some sort of change, the variables in there or the variables in here will gonna tell us their relationship before and after the change. Now, in Boyle's law, the variables that are actually involved are the pressure, the volume, and the constant value is temperature. Now for Charles' law, the variables that are involved are the volume, temperature, and the constant value is the pressure. Now for Gay-Lussac's law, the variables that are actually involved, we have the pressure and temperature, and the constant value is the volume. Now in Boyle's law, we have learned that the relationship between the pressure and volume is inversely proportional as long as the constant value is temperature. Meaning to say, whenever the pressure increases, the volume decreases. And whenever the volume increases, the pressure will decrease. That's Boyle's law. Now for Charles' law, we have learned that the relationship between the volume and temperature is directly proportional, meaning to say that whenever the volume increases, the temperature will increase as well, and whenever the volume decreases, the temperature will decrease as well. Now for Gay-Lussac's law, we have also learned that the relationship between the pressure and temperature is directly proportional if the constant value is volume, meaning to say whenever the pressure increases, the temperature increases, and whenever the pressure decreases, the temperature will decrease as well. That's directly proportional. Now this is how we interpret the equation for Boyle's law. We have here Boyle's law is equivalent to the product of initial pressure and initial volume is equivalent to the product of final pressure and final volume. That is Boyle's law. Now for Charles' law, this is how we express the equation. The initial volume over the initial temperature is equivalent to the final volume over the final temperature. Now, how did we derive from this? Basically, you just cross multiply this one. We have here volume multiplied by T2, that's V1 T2, and T1 multiplied by V2 is V2 T1. So basically, if you're gonna use this formula and this formula, they are just basically the same. Now for Gay-Lussac's law, this is how we express the equation. P1, or the initial pressure, over initial temperature is equivalent to the final pressure over final temperature. Now, same as true with the Charles' law, we can just cross multiply this one so that it will be easier for us to solve the problem. We have here P1 multiplied by T2, we have P1 T2, and P2 multiplied by T1, we have the P2 T1. And that's how we derive this formula. Okay, so I have here a problem. The oxygen tank manufacturer used to produce 5.0 liters oxygen tanks at 2000 psi and 25 degrees Celsius. Statistics suggest that 3.0 liter oxygen tank at 1500 psi more marketable. What temperature requirement is needed to produce a 3.0 or 3 liters oxygen tank at 1500 psi? Now, if you're going to look at our problem, there are more than two variables involved here. Actually, all of the variables that we have learned are actually present in this one. We have liters, that's actually the volume. We have degrees Celsius, that's the temperature, and we have psi, that's the pressure. Now see, we have more than two of the variables that are actually involved. Now if we're going to look at Boyle's law, and see if we're going if it is the correct equation that we can use to solve the problem. We can see that it is lacking of temperature, so basically we cannot solve this. For Charles' law, it is lacking of pressure, so basically we cannot solve this problem again. Now for Gay-Lussac's law, it is lacking of volume, so basically we cannot use the equation. So we cannot use any of this equation. So what we're going to do is we're going to combine those equation, or we're going to combine the idea of Boyle's law, Charles' law, and Gay-Lussac law, and that's what we know the combined gas law. What is combined gas law? Combined gas law is actually a combination of all the rules from Boyle's law, Charles' law, and Gay-Lussac's law. That is combined gas law. And this is how we express the equation. P1 multiplied by V1 over T1 is equivalent to P2 multiplied by V2 over T2, and that is combined gas law. Now, if you look at the variables that are actually involved in combined gas law, these variables are actually present to Boyle's law, Charles' law, and Gay-Lussac's law. The pressure, the volume, and of course the temperature. Now, looking at the problem that I have given you a while ago, which is this, now, and looking at the formula or the equation that I've given you, which is this, we can say that we can now solve the problem. Why? Because pressure, volume, and temperature in this equation is actually given, or are actually present. We have here pressure, initial pressure. The initial pressure is actually 2000 psi. The initial volume is actually 5.0 liters, and the initial temperature is 25 degrees Celsius. The final pressure is 1500 psi. The final volume is 3.0 liters, and we're actually solving for the T2. So we are now good to go. We can use the combined gas law formula, which is this. All right, first thing that we're gonna do is we're going to identify what are the given. Okay, given, which we have just identified, actually. Okay, so that's P1, V1, and T1. P1, we have here 2000 psi, and V1, we have here 5.0 liters, and T1 is 25 degrees Celsius. Now remember, we are solving for gas, and we need to solve 25 degrees Celsius, or we need to convert 25 degrees Celsius into Kelvin, and we will be doing that later. Let us first identify the final pressure, final volume, and final temperature. The final pressure we have here 1500 psi. The final volume we have here 3.0 liters, and we're actually solving for the temperature that is required to produce 3.0 liter oxygen tank at 1500 psi. So this is unknown. Now let us now convert 25 degrees Celsius into into Kelvin. So basically, how do we solve that? Is this. Kelvin is equivalent to degrees Celsius plus 273.15, or we can just leave as it is. We can just leave plus 273. So that's Kelvin is equivalent to 25 degrees Celsius plus 273, which make up into 298 Kelvin. So that's 298 Kelvin. So these are the given, and we are now good to go. So let us solve the problem. Okay, so solution. Always remember, start with the correct equation, and the correct equation is P1 V1 over T1 is equivalent to P2 V2 over T2. Equivalent to, let us now substitute what are the given. And these are the given. P1 is 2000, or we can just leave as it is, 2000 psi. And V1, we have V1, so that's 5.0 liter over T1, and our T1 is 298 Kelvin, so that's 298 Kelvin is equivalent to P2. That's 1500 psi, and then our V2 is 3.0 liter, and we're actually solving for T2, so we can just leave T2 as it is. And then now we're going to multiply 2000 psi to 5.0 liter and 1500 to 3.0 liter. So 2000 psi times 5.0 liter is 10,000 psi liter. We can just leave as it is, and I'll be showing you how to cancel those units later. Over 298 Kelvin is equivalent to 1000 psi times 3 liters. We have 4,500 psi liter over T2, and that's it. Okay, next is that we're going to cross multiply this, since we are solving for T2. So that's, we can just copy as it is, so that's 10,000 psi liter. We can just put open and close parentheses T2 over there is equivalent to 298 times 4,500, which makes up to 1,341,000. So wow, that's a big number. So 341,000, and you just copy the units in here, which is psi, liter, and Kelvin. Anyway, we'll be canceling all these units, the units that is not needed in here. So since we are solving for T2, what I'm going to do is I'm going to divide both sides by, I'm going to eliminate 10 million psi liter on the left side. So I'm going to divide both sides in here. So 10,000 psi liter and then 10,000 psi liter. Now since they are the same, I'm just going to cancel that out, and the one that is left is T2. So we can just put T2 over there, and we can just cancel now the units of the same. So we cancel psi, liters, and liters. So what I'm going to do is divide 1,341 divided by 10,000, which makes up to 134.1, and the one that the unit that is actually left, we have Kelvin, so that's Kelvin. So there you go, the answer is 134.1 Kelvin. So the temperature that is needed to produce 3.0 liter oxygen tank at 1500 psi is this 134.1 Kelvin.